Okay, so let's get into the homework. So this is assignment one from last week actually. Let's go through the problems. Let's see if we can get some questions answered here. Okay, so the first question, they want you to find f of g of x. Excuse me, g of f of x, which is really how you're going to read this notation right here. So like the phrasing g of f of x simply means that the exterior function is going to be g of x, interior is f of x. Now we're given a ton of information up here up top, but if you just look at what I'm telling you actually three things. I'm telling you what x value to use. I'm telling you what the f function is going to be, and of course what the g function is going to be. I know this is extra condition at the end, but that's really only going to come into play, I think, at the very end, so let's ignore that for now. One thing that you can do to help you kind of process this is go ahead and write out what this composite function is going to look like. The outer function is g of x, which is going to be cosine inverse or arc cosine. So this is going to be equal to the inverse cosine. Instead of using the variable x, we want to use the actual function f of x. F of x is defined to be sine of x. And so we're actually taking the inverse cosine of the sine of x. Now we can go one level deeper because we actually know what the x value is. And so this was actually going to be the inverse cosine of the sine, this case 2 pi over 3. Now this went from looking to a pretty crazy problem to one that we should be pretty familiar with. So what we need to do first is to figure out what the sine of 2 pi over 3 is. 2 pi over 3 is of course going to be a radian defined angle. And then once we have that, we can then plug into our inverse cosine value and do some work. But again, our first job is to figure out where the sine of 2 pi over 3 is going to be. And to do that, of course, we're going to have to go to our unit circle. So if we grab a unit circle, let's bring it over here. We're looking for 2 pi over 3. So 2 pi over 3 here is 120 degrees. We're looking for the sine value. Of course, the sine value is going to be the y value. We know that from way back. And so this is going to be 3 pi over 2, positive 3 pi over 2. And so let's slide our unit circle back over. What we just determined is that sine of 2 pi over 3 is going to be positive square root of 3 over 2. All right, so that's now our new argument for the inverse cosine. This, of course, makes sense because inverse cosine does expect a ratio. It's going to spit out an angle. Okay? And so what we need to do is just figure out at what angle is a cosine value 3 square root of 3 over 2. That's really how you should think about this function, because if we have the inverse cosine, we expect a ratio to be fed to it as an argument, and it's going to spit out an angle. Okay, so what we should be asking ourselves is for what cosine value, for what angle, is the cosine value positive square root of 3 over 2. So the answer in this case is going to be back in a unit circle. X is going to be cosine, so we're just going to go around a unit circle and try to find an x value of square root of 3 over 2. Well, here's one right here at pi over 6, so that's certainly one value. But if you look around the unit circle, it should probably occur one other place. If cosine is the x-axis value, well, certainly the x-axis value is also going to be positive in quadrant 4. So we're actually looking for two answers here. Looks like 30 degrees or pi over 6, or 330 degrees and 11 pi over 6. So those will be our two possible values. So let me go ahead and record that. So it's going to be pi over 6 or 11 pi over 6. So before we put this problem away, because those are the two possible values, we should revisit now the fact that we had a condition that the g of x value, the outer exterior value, should have a value that's bigger, that's what that sign means of course, than 3 pi over 2, which means we can actually throw out this answer. Because that answer, although it does produce a cosine value square root of 3 over 2, is not bigger than 3 pi over 2. 11 pi over 6 is though, and so this will be our final value. Okay? And again, for this particular case, let's limit our answers to one rotation of the unit circle. Let's slide over. And so explain why the inverse sine of the sine of x equals x for all values of x. Well, this is actually a pretty straightforward answer. It's going to be the same because these are inverses. So if we look at sine inverse and sine, these are inverse functions. Okay, and the explicit purpose of an inverse function is to undo the action of the function. We've seen this. You've seen this for quite a few years. Probably as early as middle school, somewhere there we started solving equations. This is the same principle that tells you to add if something's been subtracted, divide if something's been multiplied, square root if something's been squared. Those are all inverse functions to one another. I know it's weird to think of it like that, but that's really what they are. Um, and so in this case, whatever the sine function does to x is going to be undone by the inverse sine of x, and so we should just be left with x. Like that's literally what inverse functions do. That's their use mathematically, and that's how you see them pretty much exclusively for the rest of your mathematical lives. So let's move into some prep for the future kind of material. Now, if you've worked with composite functions in the past in Algebra 2, certainly revisiting here in pre-calc, but again, you just have this interior function, you have this exterior function, so it's not going to be different in spirit than the trig stuff. In fact, this is going to be a little more straightforward because we just have just regular polynomials. So here we have a definition for f of x, here we have one for g of x, and here we have the x value. So really this is just going to be some plug and chug. So the f of x value is defined to be 2x plus 2. That's also defined to be the innermost function. So what we're going to do is rewrite our g function, which is going to be x over 2 plus 9. But instead of the x's, we're going to replace it with the f function. And so instead of having x over 2 plus 9, we'll replace this x with our f of x. And so what we'll have instead will be 2x plus 2 over x, over 2 plus 9. And again, all this happened is we took out our x and replaced it with the f of x value, which is 2x plus 2. And so we now defined this as a value of x. X in this case is going to be 6. And so if we want to find g of 6, we just have to do some replacements. So this will be 2 times x plus 2 all over 2 plus 9. And so now we're just simplifying. 2 times 6 is 12 plus 2 is 14. 14 over 2 is 7, so 7 plus 9 equals 16. And so again, we're just replacing the x with the f of x because it's defined to be the interior function, simplifying that through g of x and then replacing with the value. Alright, so we want to use Pythagorean theorem code to define the hypotenuse h in the diagram below. And so we should probably first understand what this word define means. That basically just means tell me what x is. I'm sorry, what h is. It doesn't have to necessarily be like a numerical value. It just has to be like h equals. And so this is a Pythagorean theorem, which means it's going to follow the form a squared plus b squared equals c squared, where a and b can be any side lengths. In that case, it's got to be these guys. And so this will be x plus 2 square, of course. This will be y minus 5 squared, and this will be h squared. Now this is close to a definition for x. It's not though, simply because it's not h equals. But this is a quick step here. If we have h squared, the inverse is to square it, which means I'll square both sides. Now, a very common mistake is to think that this square root will somehow undo these squares, which typically is how those two interact. However, in this particular case, since these two terms are being added to one another, this x plus 2 and this y minus 5, that's not going to be the case. That's only the case if everything has been added. And so what the square rooting will do is to get h by itself, which is what we wanted. And this side is just left to be x plus 2 squared plus y minus 5 squared. Now one more thing has to happen. Since we did square root it, this answer should be plus and minus simply because we don't know which of the two versions we actually want, and we don't know that any one of them is bad since we don't have more of a context. We're probably going to only take the positive square root version, to be quite honest, but like I said, to be safe, let's leave them both there for now. All right, let's do some quick review. Factoring is something that's never going to go away for us. We got to stay good at this skill, so let's go ahead and factor these guys. The first thing I'm going to do is notice that all three terms carry a positive coefficient, which means I can take out at least a 2 out of every term. So let's first common factor out a 2, leaving as 2x squared plus 5x plus 6. This 2 is going to carry, but I should be able to now, since I have a quadratic, hopefully break it down into two binomials. So what two numbers multiply to x? Well, that would be x and x. Two numbers that multiply to 6 but add to 5 should be 2 and 3. In this case, they're both positive. We can stop the problem here because we don't know what the function is equal to, so um, we can't take it any farther as far as solving. So and it also just asks us to factor these guys, so we'll stop right there. Okay. This guy over here, we're going to take a very similar tactic. Again, if we notice, we have a 6 and a 9 as a coefficient. Those are both divisible by 3, so I can rip out a 3 out of both terms. Also, please notice that we have an x cubed and an x squared, which means they both contain an x squared. And so I can back build a multiplication problem. So 3x squared times 2x will be 6x cubed. And if I take 3x squared times negative 3, I'll get 9x squared, or negative 9x squared, because that's a minus 3. And so again, we can stop the problem right there because we're just asked to factor, which means come up with multiplication. And so our multiplication problem, excuse me, and we did that. So we have 3x squared times the quantity 2x minus 3. All right, so again, we're going to simplify the following polynomial. So we're not going to do, I mean, I guess we could do this by like dividing long ways. I don't think we need to do that though. I think we can just be clever and do some factoring of these. So let's take the top here. Let's bust it down here and let's do some factoring. This is a cubic, and so being a fully defined cubic with every single term, our best bet of factoring is going to be doing some factoring by grouping. And so we call factoring by grouping means we're going to kind of consider these two terms first, and then we're going to consider these two terms second in groups. So in the first set, we're just going to factor just what's in the red parentheses. Here I have a cubed and a square term. That means I can take out at least a square term out of both. So if I build a distribution problem, x squared times x will give me x cubed. X squared on the outside plus 5 should give me the 5x squared as a second term. And so hopefully what I should hopefully be able to do is in the second set, pull out a x plus 5 as well. So building that distribution problem backwards, if I factor out a negative 9, if we have negative 9 times x, we get negative 9x. Negative 9 times 5, we get a negative 45. And so please recall that's important because if now both terms contain this x minus 5, that becomes a common term, leaving me with x squared minus 9. So the x plus 5 is finished, but the x squared minus 9 we can further factor into x plus 3, x minus 3. And so I do that just like I would any other quadratic. And so you start to notice this as a pattern, like if there's no middle quadratic term, it'll always kind of factor in this way. Either way, the very top of that fraction, or of this polynomial, excuse me, this rational, now factors as x plus 5, x plus 3, and then x minus 3. So on the bottom, this is a little more straightforward because it's just a quadratic. So we have x times x to give us this x squared term. We have 3 and 5 to give us 15, plus 3 plus 5 will give us 18. Or, I'm sorry, 8 in the middle. And so like the last step of this is to see if anything can cancel. But if you look, we have x plus 5 and an x plus 5 as two different binomials. And we also have x plus 3, x minus 3. And so those will actually cancel one another, leaving just x minus 3 as a final simplified form. Okay. So last step, let's talk about some ACT prep. And so you can always do this by guess and check, but obviously that's not the best method. Even on the test, like guessing and checking actually will average out to take longer than if you just solve the problem mathematically. So let's just do it that way. All right, so we have x minus y equals negative 5, and we're also told that x plus y equals 1. And so this is actually a system of equations. And so there's lots of ways to solve this, but again, if we want to find x times y, we just need the values of x and y. I think we should just do linear combination / elimination, whatever your teacher called it way back in the day, which means we're just going to combine these two equations, and hopefully in that process, there'll be a term that actually cancels out. So let's combine these. So we have x plus x should give us 2x. Negative y plus y is 0, which is what we want to happen. And negative 5 plus 1 would be negative 4. So solving for x, we now have a very simple equation. If we divide both sides by 2, we'll have x equals negative 2. So we have x, we just need to find y, but luckily we have two different equations here to help us do that. I'll use the bottom one just because I prefer positive numbers. So we have x plus y equals 1, but we know now that x equals negative 2. So we have negative 2 plus y equals 1. Add 2 to both sides. Y equals 3. Okay, so we have x is negative 2, y is 3. So if we want the product xy, that should be negative 6. Okay, so here we have a very classic ACT problem. We want to find integers that follow a couple different rules. So the sum of two consecutive odd integers, which is a really important part of this, is 256. What is the value of the larger integer? Now again, we can always just guess. Like we can just start guessing numbers and see which ones work out. But I think it's actually going to be faster if we actually solve the problem straight away. Now the big thing that you have to know in this problem is how do you represent a odd integer that you don't actually know the value of? So if you don't know this trick, it's a very common one, so hopefully you can put this in your repertoire of strategies. But you got to think about like a number. Like if you just pick a number like say n, you don't know if that's even or odd. And so that we should have in your head as a question, well, how do I make sure that even if I pick any random number n, that at the end the digit I end up with is going to be a positive number. And so if you recall way back, who knows when you learned this, but positive numbers are always divisible by 2, which means if I multiply whatever number I pick, where n is just going to be some integer, by 2, that should be an even number. Well, if you think about the patterning of numbers, they go even, odd, even, odd. So if 2n is always even, 2n plus 1 is always going to be odd. And so this actually represents any odd number. Now we do want a consecutive or two consecutive odd numbers, which means we want the one right after this. And so if 2n plus 1 is an odd number, then 2n plus 3 would be the next odd number after it. And so if you just pick like a number like 4, 4 times 2 is 8, plus 1 is 9. So if I take the same 4, multiply by 2, then add 3, I get 11. And so it doesn't really, since it doesn't matter what number we do need to take, we can represent odd numbers in this way and then go ahead and operate the way they want us to operate. Now in this particular problem, they want us to take the sum of these numbers. So let's go ahead and sum these expressions. We have 2n plus 2n, which will be 4n. And then 1 plus 3 is going to be 4. These aren't being multiplied, so we don't do any kind of distribution or anything. And we want that total to be 256, so this will be equal to 256. So what we should be able to do now, since we set up a nice little equation, which is what I told you this semester, so much of our semester is going to be very little new information and then a ton of like Algebra 1. This is straight up Algebra 1, but you have to know how to set up those integers first if you want it to actually operate. Anyway, so let's go ahead and solve. We'll subtract 4 from both sides. So this is going to be 252. If we divide both sides by 4, n is going to be, let's see, 6 times 4 is 24, 1, so n is going to be 63. Now, if you're looking at your list, you're right, there is no 63 over there, but we didn't find the numbers, we actually found the value of n. And so what needs to happen now is to take this value of n, being 63, and sub them back in for n. Now, we just want the larger integer, so we're really just going to focus on this guy. So if we take 2 times 63, so we have 2n plus 3. So if we take 2 times 63 plus 3, 63 twice would be 126, plus 3 would be 129. And so in this case, it's 129. All right. So that's homework key number 1. So let's put that here. Okay. So I'm going to stop this video here. I'll be right back with key number 2.